All right, here we are again. So, what are we doing today? Well, we're going to carry on with probability theory and combinatorics. And so, let me just go back to the slides real fast. We are going to cover this material or go through more of the material. And also, I have a few very excellent videos for us to look at today. First, let me just quickly recap what we've done so far. We have introduced here what we call probability and counting techniques. Now, the first group of topics that we will be looking at in this chapter involve an area of mathematics called combinatorics, which is basically the science of counting. So we began by looking at what we call the fundamental counting principle. And what this refers to is it's if we have a collection of objects, let's say n objects, they can be arranged in n factorial ways. Okay. Um, n objects can be arranged in n factorial different ways. Okay, so we introduced this concept in stages. We started out by noting that, as an example, suppose we had a 3-car garage and we've got 3 garages and 3 cars. How many different ways can we park the cars? Okay, so each way we can arrange the cars is referred to as an arrangement because we're taking all 3 cars and simply changing the order in which they're parked. Okay, so the key detail here is that we're taking all 3 of them and finding different ways to park them. Now, we went through and listed all the possibilities, and we discovered that there are actually 6 different ways of parking these 3 cars. We also wondered if there was maybe a formula that we could use to do this directly without having to actually count them all, because this could obviously take a long time if we had enough garages. In other words, if we had, let's say, 8 garages, then this could take a very long time to figure out unless we have a formula. Now, as it turns out, we do. It's actually not a formula. It's actually a function, or an operator is what it's actually called. And it is, of course, known as factorial. Let me jump ahead here and find it. Here it is. So we introduce n factorial. This is a mathematical operator, which is defined in the following way. We start out with 0 and 1 factorial, and they're both equal to 1. After that is when it really gets interesting. Okay. For example, 2 factorial is 2 times 1, which of course equals 2. We have 3 factorial, which equals 3 times 2 times 1, which is 6. And then, as you can see, it goes on from there. We have 4 factorial, which is simply 4 times 3 times 2 times 1, which equals 24. And then we can go on from there. And you can see the pattern that's emerging. Each time, what we're actually doing is taking this number and multiplying it by itself times the previous positive integers all the way down to 1. And so here we have 120. And of course, for 6 factorial, we would then have 720. Now, we looked at our calculators and we noticed that there is, in fact, an operator on there which enables us to do this directly. So if you have your phone right there, you can check and see that if you look in the bottom left-hand corner of the scientific calculator, you'll see this button X factorial. Now, what's nice about this is that we don't need to use equal signs or parentheses. If you just type, for example, 10 and then hit that X factorial button, you'll end up with 3,628,800. Now, what's interesting is that if you notice, 6 factorial was only 720, and yet 10 factorial is over 3 million. That shows you how quickly these numbers grow. It didn't take long to get ourselves up into the millions. And in fact, we tried 30 factorial, and the number was so large that the calculator couldn't even show it directly. It had to use scientific notation. So if you recall, we ended up with this number in the window of the calculator. At the very end, after all those digits, you'll see E32, which is shorthand for taking this number and raising it or multiplying it by 10 to the 32nd power. So these numbers get large in a hurry. But again, remember what they're being used for. They're telling us how many ways there are to arrange an object. So if we had, if we were so crazy rich that we had a 10-car garage, that means we literally would have 3,628,800 different ways of parking those 10 cars. So that's kind of big. Now, you also remember we watched a video about how many ways there are to arrange a deck of cards. And that number was absolutely astronomical. Okay, so let's sneak this in here as a reminder of what we saw in the video. For a deck of cards, of 52 cards, of course, the number of possible arrangements is 52 factorial. And this equals, if you go to your calculator and type 52 and what it'll show up with in the window, let's just check that out. If you recall from the video, it's a huge, huge number. 8.066, let's say, times 10 to the 67th power. So this is why they said in the video that there are so many different possible arrangements of a deck of cards that if somebody started arranging cards at the time of the Big Bang, it would still take several million more years before they got through every possible arrangement, even at the rate of 1 per second. So it shows you what an incredibly big number this really is. So we can use these for arrangements, but then it turns out that there are other purposes to which we can apply the factorial operator. It'll come in very handy for the rest of this section of the chapter. Why is that? Because we can do other things besides calculate arrangements. Now, and of course, we did this quick example here where we had a museum that acquired these 4 cool paintings. They are just, each one is a big white canvas with a dot on it. But apparently this new artist is very popular. So therefore these paintings are worth a lot of money. And so imagine some rich person buys these and hangs them up on his or her wall. And the question is, how many different ways can the paintings be hung? Well, this is the equivalent to saying, how many ways can 4 objects be arranged? Okay, because obviously each one of these is an arrangement because we're taking all 4 paintings and just changing the order or the sequence in which they're being hanged. And so based on what we've seen before, that means that we have the possibility of hanging these paintings in 24 different ways. We're not going to list them all, but you could if you wanted to, and you can see that you will in fact have 24 different possible arrangements. Okay, now the next concept that we want to define, as you can see here, is known as a permutation or permutations. And what's different now compared to arrangements is that we are actually taking our collection of objects and then we're only selecting some of them in such a way where the order of the choices matters. That is the key right there. We have a large collection. Let's say that we have in our attic. Here would be a good example of this. Suppose that we have a collection of, let's say, 20 paintings, but only enough wall space. Wall space for 3 of these paintings. Now, what that means then is that at any given time, I have to select 3 of my paintings to start with. I have to pick 3 of them. And then in addition to that, I have to arrange them on the walls. So 2 things are really going on here. I have to decide what paintings to choose and then how to arrange them. So the question is, how many different ways can these paintings be hung? Okay, so in other words, I only can show 3, but I have 20 to choose from. How many different ways can the paintings be hung? So because the order of selection matters, each choice is a permutation. Now, when I say the order matters, here's what I mean by that. Suppose that I decide to go into my collection and I pick Picasso, Vincent van Gogh, and Andy Warhol. So I picked 3 out of 20, and then how many different ways can I hang these? I can have them in this order. I can have them in this order. I can have. So I'm running through all the possibilities. And if you notice, in all 6 cases, it's the same 3 paintings, but there's 6 different ways of hanging all these paintings. So the question is, given that I have a collection of 20 paintings, how can I choose 3 to hang on my walls? And how many ways can I hang them? So each of these choices is a permutation. Now, the number actually turns out to be quite large, but what we will do is, rather than try to write them all out, in fact, it's over 6,000. What we would like to do is introduce a formula for calculating the number of permutations. Okay, so by the way, I just want to make it clear, because just to avoid any confusion, if you notice what is not in this list is something like this. I can't do this because I've only got the 3 paintings. None of them can be chosen twice. So therefore, it's understood with this formula that I'm about to show you that none of the choices can be repeated. Otherwise, the formula that I'm about to show you would not be valid. We'd have to try something different. So it turns out that there's a formula that will let us do this directly, and I'm going to go get it for you right now. Oh, look at this. Oh boy, we have a formula, and guess what? It directly involves a factorial. Our old friend Factorial is coming back to visit us again. So the way this is written is that n is the number of objects that we have to choose from. R is the number that we actually choose. By the way, it should be clear that n has got to be greater than or equal to r. We can't choose more objects than we have. But also, it's important to note that no choices are repeated. So if that's the case, the number of ways I can choose the paintings for my wall would come from this formula. And now this is where the fun begins, because you can see, once again, we can choose or use our factorial operator to come up with the correct answer. All right, so let's apply this to this particular case. So I'll repeat the formula one more time. And in this case, remember, we had 20 paintings to choose from, and we have wall space for 3 of them. So how many different ways can I choose and hang my paintings? All right, here we go. We have 20 factorial here. We have 20 minus 3 factorial here. And so we have the ratio of 20 factorial over 17 factorial. Now, on the calculator, what you can do is this. Hit the 20x factorial, and it's very simple. In fact, I don't think you even need the equal sign. I will double check that in a second. Oh, sorry, whoops. Then we'll have 17 factorial. All right, I'm going to double check it on my calculator. And, you know, the reason why I have to keep doing this is because, of course, every calculator is slightly different. And so we need to double check each one. 20 factorial divided by 17 factorial. Oh, no. Yes, you do need the equal sign. Okay. Yes, you do. Okay. Once you hit the equal sign, you'll get the correct answer of 6840. So with all those paintings that I can choose from, that gives me 6,840 ways to show off my collection, but only 3 paintings at a time. By the way, just out of curiosity, suppose we had wall space for all 20 paintings. Imagine you live in a humongous mansion. Suppose we had wall space for all, this is just for the fun of it, for all 20 paintings. How many ways could we hang them? That would be 20 factorial, because that then each choice would be an arrangement. And if you go to your calculator, you'll see, oh my God, yes, it's enormous. 2.43 times 10 to the 18th power. Okay, remember, it says at the end E18, and that means 10 to that power. So yeah, you can see it makes a bit of a difference. If we had the room, we could hang them all. There'd be room for 20. Oh my God, 2.43 times 10 to the 18th. Instead, because we can only pick 3 of them, that leaves a space for 6,840. Okay, so let's see if there's any other examples here that we could go through. Here's one. Suppose that you live in a tiny little state where there aren't that many people who own cars. Or it doesn't even have to be a state. Suppose it's an island like Guam, which is a US territory, and there aren't that many cars on the island. In fact, if you've ever been to the Caribbean, you'll notice that in a lot of these island countries, a lot of people drive mopeds because the roads are too small to carry a lot of cars. And so it's popular for people to drive mopeds. So imagine this is one of those tiny little islands where there's mostly mopeds on the road. But let's just say only cars require license plate. Okay, so the premise of this question is that you're going to pick a license plate and you get to choose yours. All right. By picking 2 letters out of 5. None of them, though, can be repeated. All right, that changes everything. I'll show you how in a minute. But let's say that you have to pick 2 unique letters. How many choices do you have? Well, in this case, the important detail is that the order of selection does matter. In other words, license plate, for example, the license plate AB is different from BA. Okay, so in other words, clearly these are 2 different license plates. The order of selection of these letters does make a difference. That being the case, each choice is a permutation. So we can use our newfound formula. Yes, we can. This time, though, n equals 5 because there's 5 letters to choose from, and there's 2 to choose for our license plate. Now, what I've done here is I've written out all the possibilities for you. So we know already what the answer is. This is the hard way. What did I do here? I wrote them all out. And that took a while. We don't like to do this. This is very tedious and boring. And if you notice, like I said, A and B and B and A are both listed separately. The same thing could be said for, let's say, B and D and D and B. They are considered to be unique license plates. So these are all permutations. The question is, how could we figure that out from our formula without having to list them all? Okay, let's see, where did I do that? Oh, here we go. I've got it in the wrong spot. Hold on a second. Here we go. So in the license plate example, N is 5 because we had 5 letters to choose from, and R is 2. And so when you plug in those numbers into this formula, you'll see that it does indeed give us 20. Okay, so just for the practice, why don't you plug those numbers into your calculator and make sure you're getting the same thing. Okay, now let's just take a side note. Just as a side note, I just want to mention here, and they'll make in the videos that we'll be watching later on, they will talk about this as well. Imagine though this time, now remember with the paintings, you've got one, let's say, painting from each artist, and you obviously can't pick the same painting twice to hang on your walls. This is a different situation. Okay, in this case, suppose that we allow for repeated letters. For example, AA, BB, CC, DD, EE are now valid choices. How many permutations are now possible? Okay, well, we've added 5, so you have 25. So the formula we used before is no longer valid. It's only showing us permutations when there's no duplicates allowed. So how would we figure this out with a formula given that suddenly we're allowed to have duplicates? Okay, so if duplicates are allowed, then the number of possible license plates is 5 times 5. Okay, in other words, for each plate, each letter, there are 5 possibilities. So in other words, instead of using the formula we had a few minutes ago, instead all we would do is multiply the number of choices we have, which is 2 letters. For each we have 5 choices, so we'd multiply 5 by 5. So the number goes from 20 up to 25 now. But that's only if we allow for the possibility of duplicate selections. In some examples, that will be the case, and in others, it will not. Okay. Now, just for the fun of it, let's try this case. Suppose that the government runs out of license plates. They're all taken, okay? License plates. In the sense, not that they can't make them anymore, but they're all taken. So now the residents can choose 5 letters out of the entire alphabet. But we'll assume right away with no duplicates allowed. How many license plates can now be created? Okay, so now N is 26 and R is 5. Now remember, no repeats. All right, no, we can't have any repeated values. So how many choices do we have? All right, well, we're going to use our permutation formula. So we have 26 for N, R is 5. So we have the ratio 26 factorial over 21 factorial. Now, those are both enormous numbers. So in your calculator, what you want to do is put 26 factorial divided by 21 factorial. Don't forget the equal sign. And you should get ooh, that's a big number. 7,893,600. All right, did everyone get that? 26 factorial divided by 21 factorial equals 7,893,600. Now, what if we allow for duplications in the letters? Okay, suppose that duplicate letters are allowed. How many license plates can be created now? So in other words, all 5 A's would be a valid choice. So here it would be 26 times 26 times 26 times 26 times 26, because there are 5 letters. We choose 5 letters, and there are 26 letters to choose from. So you're going to see that it's going to be a much bigger number, like preposterously big. Let's check it out. So basically on your calculator, well, it's not, okay, it's not as ridiculous as I thought. You can do this on your calculator. Well, first, it's 11,881,376. But on your calculator, what you can do is just do 26 exponent 5 equals, and you'll have your answer. All right. Now, let's look at another example. Suppose, in this case, we have the students of SUNY Purchase have decided to start up a math club. But in order for the school to approve the club, they have to have a list of 3 officers. One is the president, one is the vice president, and one is the treasurer. Now, nobody seems to care which job they have, if any. So we're going to randomly select people for these jobs. So every student will be assigned a number from 1 to 10, and then we will randomly choose 3 of those numbers. The order in which we select the numbers will determine who fills each position. Okay, so for example, what if I randomly choose the numbers 3, 1, and 7? That means that student number 3 is the president, student number 1 is the vice president, and student number 7 is the treasurer. All right. What if instead I had chosen the same 3 numbers, but instead of 3, 1, 7, I picked them in this order: 7, 3, and 1. So you can see this matters a great deal because now student number 7 is the president, student number 3 is the vice president, and student number 1 is the treasurer. So what we're saying here is that these all represent permutations because the order in which I select the numbers matters. So if I want to know how many ways I can fill these positions, what I'm really asking is how many permutations can I create when I pick 3 students out of 10? Okay, it means the same thing. So once again, we'll use our example, our formula. And so remember here we have 10 students of which we're choosing 3. And if you plug in the numbers, you'll see that it turns out to be 720. And of course, down in the bottom, I've filled in the how do you do this on your calculator? 10 factorial divided by 7 factorial, don't forget the equal sign, and you'll end up with 720. All right, I have one more example here. This involves horse racing. Now, clearly, with a horse race, what typically happens is that there are prizes for the horse that finishes first, second, and third. Now, when I say prizes, I mean not for the horses, but for the gamblers who are betting on the race. The horses don't care. They just go back in the stall and eat their hay. When they win, they don't have no idea what's going on. They just run. Somebody tells them to run, they run. Okay. So anyway, but the gamblers who are sitting in the stands are watching these horses very carefully because the order in which they finish will determine how much money they win. For example, what if we had a situation where there's 8 horses in the race and I buy a ticket. Let's say I go to the racetrack and I buy a ticket that says 1, 2, 3. That means I'll win money if the first horse finishes first, the second horse is second, horse number 2, I mean, and horse number 3 finishes third. If instead horse number 2 comes in first, horse number 3 comes in second, and horse number 1 comes in third, I don't win if I have this first ticket. The order determines whether I win or not. So the number of different ways in which the horses can finish in first and second and third place is a permutation because the order matters. The question then is how many bets are possible on this horse race? So what we're essentially saying is how many permutations can we create by choosing 3 objects from 8? All right, and so you can see the formula is here. I've plugged in the numbers. N is 8. R is Whoops, sorry. R is 3, my fault. Hold on. And so this reduces, as you can see, to 8 factorial over 5 factorial. And when you plug that into your calculator, you will, in fact, end up at 336. That's how many different ways you can bet on this horse race. Now, again, you notice the one thing we did not, and I forgot to mention this with the last example, earlier when we had the letters and the license plates, we had to make a separate case for when the letters could be repeated. With this situation with the students, that can't happen. You can't pick student number 3 to be both the president and the vice president. So it's not possible to have any repeated choices. So we can just go ahead and use this formula directly. The same thing with the horse racing. You can't have horse number 1 finish first, second, and third. So we don't have to worry about that situation arising. No repetitions are possible. But when they are possible, we have to use a different formula. Okay, so I just want to mention that right here. Now, with all that being said, we've had tons of good examples here. Yeah, no, let's assume that that's not going to happen. Yeah, I see what you mean. Yes, student number 3 could theoretically fill both slots, but let's just say that that's not allowed. Just to get that straight right up front. So what happens when we choose objects in such a way that the order does not matter? Then they're no longer called permutations, they're called combinations. And there's many scenarios where we could end up with combinations instead of permutations. All right, so if there's selections where the order does matter, there can also be selections where the order does not matter. Okay, now here's a good example of this. And I think you'll find this a very good example because everybody knows and loves the products of this company. And that company is Haagen-Dazs. What do these guys specialize in? They make fantastic ice cream. By the way, you know what, just in the other class, just for the fun of it, I looked up, I was thinking, I wonder what country this company was founded in. It looks like some Scandinavian thing or other. Well, it turns out that it is no such thing. It's based in the Bronx. Somebody decided it would be cool to give it a very exotic, foreign sounding name to get a lot of attention when they first opened up the company. And it certainly worked because nobody could ever forget this, Haagen-Dazs. In fact, if you watch some of the earlier commercials that they had, the whole premise of the commercial is it's hard to pronounce us, but it's worth it. That's that's marketing, baby. You know, I mean, if you're interested in marketing, this is a classic example. Why don't we call ourselves some exotic sounding name? You know, people will assume it's from Denmark or Sweden or Norway. They'll think our ice cream is really exotic, and it is, but we have to convince them of that to get them in the door. And once they're in, we'll sell them on our wonderful ice creams. And so, yeah, I mean, that was pretty much a stroke of genius. Now, I mentioned the other class, there is a TV series on where each episode typically involves food companies. And there might actually be an episode, now that I think about it, about Haagen-Dazs. And what happens is each episode is about one type of typically snack foods that we know and love, but we may not know the history of the company or how this product came to be. And so, for example, one week they had an episode about Wise potato chips. And another week they would be talking about Hershey's. And, you know, they have all these excellent episodes which explain how these products came into being. And in some cases, it was almost an accident by which it was discovered that this thing that they're selling would be very delicious. Oh, I don't think I've ever seen that. Lipton brisk iced tea. Sometimes advertising is very well done. It's very interesting. And sometimes it's just crap. You know, you see all extremes all day long on TV. There's all kinds of wonderful ads and all kinds of awful ads. And you just don't know. But sometimes, unfortunately, the bad ads sell the product. And so that's why we keep seeing more of them. Yeah, I mean, Sometimes, in fact, even their strategy is to annoy you because that way it'll stick in your memory. Yes, I mean, I agree. There's a lot of really dreadful ads out there, but remember, their job isn't to entertain you, but to sell you on the product. So just keep that in mind when you watch dreadful commercials. I know. It's really, uh, you tell me what an emu has to do with anything. But the fact that they keep repeating these commercials over and over again means that they must be succeeding. Otherwise, they would have to pull the plug and try something different. There's no way they could spend all that money in advertising if it wasn't working. So, emus are selling insurance. Well, whatever. It may just be that it's such a weird bird that people notice it when they see it. And that's why it's working. That's right. If it works, it works. You can't ask why with advertising. Just does it work or not? Okay. It doesn't have to make sense. As long as it works, that's all that you care about as the company. All right. But anyway, so let's say we show up at a Haagen-Dazs and they're having a special promotion. If you buy an ice cream, you can get any 2 of these 5 toppings available for free. Oh, look at these goodies. Gummy bears, Oreos, Reese's Pieces, marshmallows, sprinkles. Now, here's the big question. If you pick, for example, gummy bears with marshmallows, does the order in which you select those 2 toppings have any influence on the taste of your ice cream? No, because they're just going to take the toppings and dump them on the top anyway. The order of selection has no bearing on the taste of your ice cream. So each choice that you make is now going to be considered to be a combination rather than a permutation. And if you look at the list of possibilities, you'll see what I mean. This is all of them. And of course, I've abbreviated them all with a letter. So this is gummy bears and Oreos. And what you'll notice that's missing from this list is OG. I don't need to list it separately because they mean the same thing. And so because of that, there just aren't that many combinations. There's only 10. With permutations, everything has to be listed. I would have needed OG and RG and MG and all the rest. Here, the order is irrelevant. So therefore, there's not as many combinations as there are permutations. Anyway. Now, by the way, since we have a minute here, I just wanted to mention a very amusing anecdote from the history of math that you might find interesting because it gets into this idea of the order mattering or not mattering. This is an anecdote. I think you'll find this interesting. I don't think there's a video. I wish there was. It would be a lot of fun. But in fact, let me see if I can find a video about this. Okay, well, there's the tea lady, but I should have gone to YouTube. There, okay. I said I don't want it to be too technical though. All right, I'll tell you what, let's check this one out. It looks like it has some promise because this is a true story. What reminded me of it is this idea of the order mattering or not mattering. What happened was, and I'll throw this in here for you, the statistician Ronald Fisher, and by the way, he is one of the big heavyweights in the field of statistical history. He invented a lot of what we use today. So the statistician Ronald Fisher was at a tea party or a party in the early 20th century, because that's, when he lived. Okay, now he met a woman who claimed that she could tell the difference between a cup of tea, and now we're assuming here that I don't know how you take your tea, but this lady was drinking milk with her tea. Some people like it that way. So she claimed that she could tell the difference between a cup of tea where the tea had been poured first and a cup where the milk had been poured first. Okay, in other words, she's saying that to me, it matters a great deal if you put the tea and then the milk, or the milk and then the tea. Okay, now, does this seem plausible? I mean, after all, they're just going to, swirl themselves together. And so Fisher devised an experiment. Now, this guy's a statistician. He can't help himself. As soon as he hears this, okay, so Ronald Fisher decided to conduct an experiment to test her claim. He had 8 cups of tea prepared. Now, of course, this is without the lady being in the room while this is going on. In half of the cases, half of the cups, the milk was poured first. And in the other half, of course, the tea was poured first. The lady was asked to taste all 8 cups and identify which ones had the milk poured first and which ones had the tea poured first. Okay, now, here's my question to you. What do you think happened?
She couldn't tell. There's no way.
Okay, well, I'm going to tell you what actually happened was the lady got all 8 right. Fisher therefore concluded that she did indeed have the ability to tell the cups apart. Now, this story is a lot deeper and more complex than this, but this is in a nutshell what happened. In fact, this was part of the foundations of what he developed as far as statistical inference, which we'll be discussing in chapter 12 anyway. So I feel like this story is not a waste of our time. But the fact that she was able to get all 8 of them right, if she'd been guessing, then you would expect her to get 4 right and 4 wrong. But the fact that she got all 8 of them right means that it looks like she does know what she's talking about. And now how she did it, we don't know. I mean, I don't understand either how this is possible. But apparently this lady was such a tea aficionado that she developed this ability to tell them apart. Now, so Fisher concluded, now there's still a chance. I mean, 8 out of 8 is a very good result. If you know what you're doing, you should get them all right. If you don't know what you're doing, then you expect some of them to be wrong. It's still possible that she got all 8 of them right by pure luck, but Fisher concluded that that wasn't likely, and therefore she must know what she's talking about. And this led to a lot of important results in statistics. But I'm hoping that this video will explain it in a fun way. So let me send it, because I haven't watched this before. I just found it myself by accident. So I'm going to send it to you. It's only about 2 minutes long. Let's check this out. And okay, so hold on. I hope it'll be fun. But now you know what's going on. So there it is. And let's check it out and see how well they explain this. All right. Well, I'm glad to see that was a lot of fun, and you got the idea. Now, that video really is more appropriate for our stats chapter, but I thought it would be fun to watch it today because the reason why I brought it up is because we were having this discussion about whether the order matters or not. So with our Haagen-Dazs example, we said, well, the order doesn't matter. But if we were talking about tea, then maybe if you were allowed to choose milk first or tea first, then maybe the order does matter. And then we would end up with permutations rather than combinations. But except for somebody like that who really knows her tea, I think you'll agree that in this case, the order does not make any difference. I can hardly believe anybody would notice it if the guy behind the counter poured the gummy bears first and then the marshmallows, or the marshmallows and then the gummy bears. I don't believe anybody could really tell the difference. So therefore, these qualify as combinations. Anyway, so let me, fun historical side note. Okay, that's what I'll call it, a fun historical side note. The thing is, what's interesting, people don't realize in general that the history of math and statistics is actually far more interesting than maybe we generally realize. A lot of very interesting results have taken place purely through accident. And this is one of those cases. And he did, like I said, he did have to sit down and think, I randomly picked 8 cups. Maybe I should have had more, maybe less was enough. And so he really developed a lot of important ideas from this situation. So I don't know. I thought that was quite interesting. Anyway, so in the case of the Haagen-Dazs, we did note that there were 10 combinations. So hopefully there's a formula somewhere out there that we can use to come up with this number rather than counting them all ourselves. And in fact, there is. Let me show it to you. And it's a little bit messier than what we've been dealing with. And in fact, I wrote the formula for permutations directly below so you can see where they're different. And in fact, there's only one place with the combinations formula, we have this extra r factorial in the denominator. And that's the only difference. Okay, so write that down. And then we're going to go back to that Haagen-Dazs example and prove that the number of ways of picking 2 toppings out of 5 with no, and by the way, we're assuming here none are repeated. You don't pick 2 marshmallows, for example. We're going to find out what happens in that case. All right, so let's take a look at this. We're going to plug in the numbers. So here n is 5 and r is 2. So we plug in the numbers, and you can see that in the denominator here, we have the product of 3 factorial times 2 factorial. And when we work through the math, we can see that we end up with 10 combinations that we can create when we have 2 toppings to choose from out of 5. Now, I've also come up with another couple of examples of this that I think you'll find interesting. For example, in card games, let's say, for example, you're playing draw poker. Now, with draw poker, you've got 52 cards. Every player is dealt a hand with 5 cards. Now, the order, whether you play cards or not, it should be clear, when you get a hand of cards, the order in which they're dealt to you does not affect their value. So each hand could be considered to be a combination. The order is immaterial. So what we'd like to know then is, with a standard deck of 52 cards, how many different hands can be created when we deal out 5 at a time? Okay, so in that case, we would have a situation where we're trying to figure out how many combinations there are. And of course, n is 52 because the deck has 52 cards. R is 5 because we're choosing 5 at a time. And so my challenge to you is to come up with this number based on this formula and the values of 52 and 5. All right, so once you take a minute, get out the calculator and see what you can do. All right, well, let me show you how it's done with the calculator. In the bottom, those are the keystrokes. What's different now is that you have a product in the denominator, so you'll need a set of parentheses. Well, first of all, the answer is 2,598,960. How do we get that? We have 52 factorial first, divided by, and then you must open parentheses for this, 47 factorial times 5 factorial, close parentheses, n equals will give you the correct answer. All right, so if you try that, plug in those numbers and make sure you're getting the right answer. All right. So we've got one more. This is a very similar case. What we're going to do is now switch over to a game of 3-card poker, where instead of each hand containing 5 cards, it'll only contain 3. The question is, how many hands are now possible? So it's going to be very similar to what we just did. Oops, here it is. Okay, so in this case, the only difference is that R equals 3. And if you plug in the numbers, and you can see down here the keystrokes you need, you will end up with only 22,100 this time. Let's see, don't forget that equal sign. All right, so make sure you can go through and come up with this number. Okay. Does everyone have it? All right, now, is everyone done with that? I think we're now ready. I found 2 really outstanding videos that really tie together everything we've done today, and the other day too, of course. In other words, arrangements, combinations, and permutations, plus the factorial operator. They do a really nice job of explaining them and also raising questions about what we're doing and how we know that it's being done correctly. So, but it's also fun. Okay, most of the examples he gives are kind of amusing, and especially in the second one. So, all right. So if we're all ready, I'm going to post the first of the 2 videos, and I think you'll agree that they're a lot of fun. All right, let me grab the first one, which is called Permutations. And that one will be followed by a second video, which is called Combinations. All right, so we're going to cover everything here. All right, let's check this out. So there's your video. There's the link. And I'm going to, of course, turn off the sharing. And let's check this out. I need to find the best way to learn about this song. Hi. Let's take a look at an example, and we'll see if that helps clear up this. Your town has All right. Well, that was kind of intense, but we'd already covered the background material, so I'm hoping that that added some understanding. The combinations one is a little bit more fun, I think. So let's check this one out. All right, there you go. sure. Let's check our work with the old method of writing out the combinations. So we start with an outline. Different paths. All right. Well, that was kind of a lot, but now that we're done, I mean, I think we're really very comfortable with these concepts. And so next time we're going to switch over to something a little bit different, which is probability theory, which is also extremely interesting. And of course, the foundations of probability theory are based on what we've just been doing here. So it's important to have this background before we start probability theory itself. All right. In the meantime, between now and next Monday, and by the way, I forgot to wish the other class a happy Easter. All right, I'll wish that to you. But next Monday, all you have to do, we'll just come back and carry on with chapter 11. So right now, all you have to do is just make sure you understand what we've been doing up to this point in chapter 11. All right. Other than that, if there's no last minute questions, I'll see you all on Monday.
Thank you.
Okay.
Thank you. Have a good
All right.
weekend.
See you later.
Thank you.
Bye.